Hi, I'm Seung-Hwan, a postdoc at Princeton. I'd like to talk about how we could extend BRDF for polarization. Human vision system can capture the intensity of light in visible spectrum. Interestingly, there is a thing that our eyes cannot see, but these living creatures can. That is polarization, a wave property of light. As an electromagnetic wave, light propagates where its electric field oscillates in space. The oscillation pattern projected to the tangent plane describes the polarization state. It could be polarized in a linear, elliptical, or circular way. Any polarization state of light can be described as a 4x1 vector called Stokes vector, where each element means intensities of light and 0, 45 degrees linear components and circular component. The change of polarization can be described as a 4x4 matrix called Miller matrix. For example, the Stokes vector of light incident to this linear polarizer changes to another Stokes vector. Multiplication of a Stokes vector and a Miller matrix mathematically describes this procedure. While human vision cannot sense the polarization of light, modern imaging devices allow us to capture polarization. For example, if an unpolarized light, a mixture of random polarization states, passes through a linear polarizer, it becomes linearly polarized. Quarter wave plate operates on the perpendicular electric field components. It shifts one of the components by the quarter of wavelength. Using this, a linearly polarized light can be converted to circularly polarized light. So, why do we capture polarization? Because it enables in-depth scene analysis. Examples are reflection removal, descattering, shape and appearance imaging for challenging objects, and segmentation and detection, such as cancer cells. All applications rely on how polarization state of light changes after reflection on object surfaces. For an ideal mirror, linearly polarized light remains as linearly polarized following Fresnel reflection. If the object has ideal diffuse reflectance, the light becomes unpolarized after reflection. Then, how does the reflection on real-world materials change polarization? To understand the problem, let's first review BRDF, bidirectional reflectance distribution function. BRDF is a scalar function that describes how the light intensity changes after reflection on an object. BRDF measurement datasets of the real-world materials have played a critical role on understanding and modeling the BRDFs. Polarimetric BRDF, so-called PBRDF, is an extension of BRDF for polarization. PBRDF is a matrix function that returns a Miller matrix for given directions and wavelengths. It describes how polarization state changes after reflection. As a superset of BRDF, PBRDF is a complex function that requires careful analysis through real-world datasets. Unfortunately, existing PBRDF datasets are limited for this purpose because they only support a small directional region, can only support for either linear or circular polarization, and have only captured a few materials to date. In this project, we aim to solve this problem by capturing a first comprehensive PBRDF dataset of 25 real-world materials. Our dataset has large directional coverage and describes complete polarization change necessary for analysis and rendering. To capture this dataset, we had to develop an imaging setup that satisfies 4 design principles. First, we want to acquire PBRDF at every direction for analysis and rendering. Second, we want to capture the complete polarization change as a Miller matrix in terms of both linear and circular polarization. Third, this PBRDF should be acquired per each narrow spectral band because polarization is relevant to spectrum. Lastly, capturing PBRDF shouldn't take too long. Existing PBRDF imaging systems take months for capturing a sample, which is impractical to acquire PBRDF of multiple materials. We achieve these goals through a novel combination of 2 well-developed techniques in computer graphics and optics: image-based BRDF acquisition and spectroscopic ellipsometry. This allows us to meet all our requirements, capturing the comprehensive PBRDF of a material within 3 days. This is the acquisition system that we built. Light source emits light to the sample, and the camera captures the reflected light. A homogeneous spherical sample is placed at the center. Note that we want to know the PBRDF-M of this material. A rotating arm is attached to a turntable that rotates from the opposite side of the camera to the front. In the rotating arm, we have a polarizer module. The polarizer module has an LED light source and a lens that emit unpolarized light. A linear polarizer and a quarter wave plate changes the polarization state of light. We modulate the polarization state by rotating the quarter wave plates 36 times, resulting in the Stokes vector P as a function of the rotation angle. Next, we have an analyzer module, which is separated from the turntable. The analyzer module has a spectral filter wheel with 5 spectral bandpass filters. We then have a quarter wave plate and a linear polarizer that enables the complete polarimetric analysis of incident light by rotating the quarter wave plate. Polarimetric change by these analyzing optics is modeled as a Miller matrix function A, depending on the retarded rotation angle. Similar to the polarizing optics, we set 36 different angles. The light is then focused by a lens and captured by a monochromatic camera. In summary, the emitted light from the polarizer module is modeled as a Stokes vector P. It changes to MP after reflection and captured by the analyzer module as AMP. We capture this at multiple configurations with 36 retarder angles, 147 turntable angles, 5 spectral filters, and 8 exposure levels. Overall, we capture 200,000 pictures for a single material. From the captured data, we now want to reconstruct PBRDF. For each turntable angle, wavelength, and pixel, we have an observation vector F with 36 different retarder angles. For each retarder angle, we know the Miller matrix of the analyzing optics and Stokes vector of the polarizing optics, and we estimate the material PBRDF-M by solving an optimization problem. This shows the estimated Miller matrices for all parameter combinations. We finally obtained the PBRDF table parameterized with wavelengths and 3 directional angles for 25 real-world materials. This dataset is easy to use for rendering and analysis. So, using our PBRDF dataset enables physically accurate rendering of intensity as well as degree of polarization, indicating how much the light is polarized, and type of polarization, whether the light is circularly polarized or linearly polarized, and cellularity of polarization, indicating the handedness of circular polarization, and angle of linear polarization, which tells the angle where the linear polarization happens. In addition to rendering, our dataset can be used for analysis of the media reflecting light. For the materials in our dataset, we investigated how polarization is related to various material appearance parameters, such as surface normal, surface roughness, material type, and color. Here, we will introduce 3 interesting analyses of them. For more details, refer to the paper. First, let's look at normal and polarization. For this dielectric white billiard ball, points with different surface normal have different AOLP values indicated by different colors here. For the metallic chrome, AOLP does not vary that much as a function of surface normal. What we observed in our dataset, interestingly, COP of this chrome material shows normal dependency. This suggests to use circular polarization when we estimate the shape of metallic materials. Next, we examine the impact of surface roughness on polarization using rough spectralon and smooth ceramic materials. In the AOLP, the normal dependency of ceramic material is stronger than spectralon material. This suggests that there is correlation between roughness and polarization, which can be exploited to infer roughness from polarization. Next, we are going to see the difference between dielectric fake material and metallic real gold. While they look similar in intensity, the cellularity of polarization of the samples are opposite, providing a new effective way of detecting the type of material. In conclusion, we proposed a practical PBRDF acquisition system and captured a first comprehensive PBRDF dataset of 25 real-world materials. It can be used for various polarization researches. Please visit our project website for more details, and thank you for listening.